Welcome to Math 303D, Introduction to Abstract Algebra. I am Unkaila Dasmani, your course instructor for this course. For the syllabus for this course is very interesting. So in this course, we'll be covering some topics such as mappings and binary operations, relations on sets, algebra for numbers. We also look at number system, complex numbers, algebra structure, groups, ranks, and a lot. So, but in this particular unit 1 of this course, we are looking at mappings and binary operation. Mappings and binary operations. So in this unit 1 and in this video, we are looking at section 1 of unit 1. So in this section 1, you'll be learning how to describe a mapping and how to distinguish between and among the various classes of mappings. Let's look at the objective for this course or this session. The objective of this session is to explain what a mapping is, determine the rule for finding a given mapping or rule for a given mapping. Then you have to describe the classes of mapping, that is injective, surjective, and bijective mappings. Good, let's go. What is mapping? Definition of mapping. What is mapping? So how do you define a mapping? You've heard about mapping before. So let's see the diagrams, the diagram on the board. We call this diagram an arrow diagram. So the diagram in this figure 1 represents a mapping from set A to set B. So you can see set A is here to set B. Okay, so this one is an arrow diagram. Set A is called domain, so we call this domain, and then set B is called domain. Good. So now let's think of this arrow diagram here. Let's assume that the name of region in Ghana and their capitals. So you can see that the capital of Western region is Takoradi, capital Greater Accra is Accra, Northern region Malibona Hafo, then you can also think of Sinjani. So do you think of how this came by? How did it come by? So you can see that it's following a certain pattern, and actually it's something that talks about a rule. So let's look at the next one. So you can see that the Takwa, the Accra, Tamale, and Sinjani, they are what we call the set of the images or the codomain, as I've written there, and then the other is the domain. Okay, let's see the next slide. So based on what we have seen, we can see that a mapping is seen as a rule which connects each element in the domain to one element in the codomain, because we're having the regions in their capital. Asante region, you cannot go and say Mampong. No, there's a rule for that. Greater Accra was Accra, and the rule was that regions in their capital. Okay, so let's see if the diagrams there, the arrow diagrams there, we have 4 of them, if they are mapping or not. Because mapping is now a thing of being a rule which connects each element in the domain to one element in the codomain. So A, can you say A is a mapping? Of course. We have each element in the domain here is having a corresponding and only one corresponding element in the codomain, the codomain. So meaning that you can say that it's a mapping. That's the B. Is B a mapping? Of course, B is not a mapping. What is the reason? Because of this 3. This 3 is not having a corresponding image here. Then if you violate the rule, then we can say that it's not a mapping. Let's go to C. What can we see about the C? What can you think? What do you see? To see a mapping. Okay, let's see what happened to this one. the number 1 is having more than one image, but the rule is saying that each element in the domain to one element in the codomain. So here we're having 2 elements in the codomain. Because of that, we can say that actually not. It's not a mapping. Let's look at D. What do you see about D? You can see that 0 is having 3, 1 map to 3, 2 map to 3, 3 map to 5, and then 2 map to 3, 3 map to 5, and then at 7, 2 and 7 here, they have no corresponding domain, but that is not our interest. Our interest is that each element in the domain should map to an element in the codomain. So this one is actually an example of mapping. You can think of it's an actual example of mapping. So you can say that this is a mapping. Thank you. Let's move on to the next slide. We can also write a mapping as a set of ordered pairs. So like the arrow diagram. So here you can see the domain, and then this is your codomain. So actually these are the set of ordered pairs. So 1 map to, oh sorry, not cancel, let me delete that. So 1 map to 3, 2 map to 5, 3 map to 7, 4 map to 9, and then 5 map to 11. Set of ordered pairs. So another way of describing mapping. Good. Okay, a mapping can also be likened to a number machine or formula in which you put initial value, let's say x, and then comes out a result or an output. So in that instance, we can say that a mapping can also be represented by a function. So looking at this arrow diagram here, so you can see that we have algebraic relation here. So either algebraic relation or a function. So this mapping is actually assigned by this rule, 6x plus 2. We take the input, initial condition 0 input into this machine or preset, then what will be the output? When I put 0 there, the output is 2. When I put 1 there, I get 2 outputs. And I put 2 there, I get 14. Let's say it's a machine, a product, and it means I want to put 2. Let's say when I take 2 labor, they can produce 14. When I take 1, they can produce 8. If I pick no labor on that day, the machine alone or only the owner alone, I am the owner, so me not employing anybody on particular day, I can produce 2 output. But when I employ 1 person, can produce 8. When I employ 2 persons in addition to me, we can produce 7. So actually it can be represented by a function that is also a mapping, which can be represented by or as an algebraic expression or algebraic relation or a function. Great. So types of mapping. Here we want to consider only 3 types of mapping, then the rest you can find them yourself. First of its type we want to consider is one-to-one mapping, and then we want to look at many-to-one mapping. So for one-to-one, each input value of x maps to only one output value of f of x. So you can see that all the previous slides we've seen a one-to-one function. The first one we see, you can also see the regions and their capital, actually one-to-one mapping. Okay, so what then is the many-to-one mapping? For many-to-one, many values of x give the same value of f of x. Many values of x give the same value of f of x. So let's see this function or mapping. Because of this expression, I can say it's a function. So we take 0 input into this processor machine, we get -2 output. Then I take -3 into that process, I get the same thing. So many-to-one, many values of x give the same values, and similarly many values of x -2 -1, they give the same value of -4. then we can think of this to be a many-to-one mapping. Think it's very clear. Don't forget these are our codomain, and then this one is our domain. Great. Okay, that's fine. Let's look at the next slide. Finding the rule of mapping. How do you find the rule of mapping? Now, you define mapping as a rule which connects each element in the domain to one element in the codomain, right? So how do you then determine such rule? How do you determine such rule? So let's use this arrow diagram to find the rule. So first, these are the steps. Note these steps down. First step, find the difference between consecutive elements in the domain. Now, when you come here, you can have our domain here. Alright, so let me say domain here, domain, and then co-domain. Okay, so find the difference between the consecutive terms. I can say 1 minus 0 equals to 1, then 2 minus 1 equals to 1, 3 minus 2 equals to 1. That's the first step. Second step, find the difference between consecutive terms in the codomain. We did find first between the domain. I want to find between the codomain. That is 3 minus 1, I get 2. And then you can also think of 5 minus 3, I get 2. Here is 2. And then 7 minus 5, I get 2. That's good. So that is second step. First step is here. That is step 1. Step 1, and then here is step 2. You find the difference between step 1, difference between consecutive terms in domain. Step 2, difference between consecutive terms in the codomain. Okay. So what is then? What do you do next? Okay. Now, looking at this, we see that the difference between the consecutive terms in domain, they are constant, and the same happen to the codomain. So in this instance, we can say that the rule of this mapping is a linear. The rule of this mapping is a linear. And the reason is the difference between the consecutive terms are all constants. Once a linear, now you can think of the rule to look like a linear function. Ax plus b, this is a linear function. Where b is our intercept, a is a gradient. You remember that? Okay, so let's look for the next graph, the next video for. So the next video, so as I said, the rule looks like this, a linear graph, and we can also see this a is a gradient, and the gradient is actually found as the difference between the constant element of the codomain, or divided by constant difference in the element of the domain, that is changing y over changing x. And when we do that, we get changing y we had 2, changing x we had 1, and we get 2, and the 2 is here. Now putting that into the function, we get x maps to 2x plus b. Now after getting that, how do you find a b? Let's look at the next slide. For b, these are the domain and then corresponding images. So you choose any of them, you put into the function, you get your b. So here I've selected 0 and 1. 0 and 1. It means that x mapped to 2 times 0 plus b. So x is 0 here, and then it will function as x, that is 2x. So 2 times 0 plus b. So when you get b equals to 1. Now putting b equals to 1 and a equals to 2 into the linear function, we get this, or this as a rule for that mapping. That's very interesting. Now check it out. Find a rule for the following mapping. You use the same procedures, the difference between the constant terms, So here you can see that you find the difference between the constant terms of domain, that is A, and then you also find the difference between constant term of the codomain, so that is A. So you get A to be equal to 3, then you put the 3 into the function, then you get x maps to 3x plus b using any of the values, either this and this, or this and this, or this, and any of them at all. Putting them into that, you get for b to equal to 2. Therefore, the rule for the a here, the rule for this a here is 3x plus 2. 3x plus 2. Good. So you can also find the rule for the b. Try it. So you get 2x plus 2. The rule for this one is 2x plus 2. Try it. And let's see. X maps to 2x plus 2. Thank you. Let's check out for the next. The next we are looking at injective, surjective, and bijective mappings. That is various classes of mapping. So what is injective mapping? Let's look at definition. Suppose that x and y are any two sets. Let f of x map into y be a function, then f is an injective mapping. We also call it one-to-one. If whenever x1 and x2, they are all members of x, as such that f of x1 equals f of x2, then x1 equals to x2. So when you have x1, x2 all be a member of the big X, and you also have this fact that f of x1 equals f of x2, which implies that x1 equals to x2, then you can say that this mapping is actually an injective mapping or one-to-one mapping. Thank you. Looking at this example, you can see they have the domain here and they have the codomain here. So domain 1 is having image 3, 2, image 5, 3, image 6. So you can see that it's injective mapping, and the question is why? Why? Because each element in the domain is having a distinct value. In the codomain, then you can say that it's injective mapping. Now let's look at the second one. Would you say it's injective mapping or bijective? Okay, now no injective mapping. Would you say this function is injective mapping? Okay, the answer is certainly no. It's not injective mapping. What is the reason? Okay, and the reason is this x. So this x is having a, c, and then d. All these three maps to z. Z is having more than one element from domain. With that instance, we say that this is not one-to-one, or it's not injective mapping. Good. Surjective mapping. Another term. Suppose that x and y are any two sets. We have f of x being a mapping, f being a mapping of x, y. Let's that one be a function. Then f is injective mapping. Another name is onto mapping. If for every y, small y in y, there exists small x in x. Now this depends on the choice of y actually, such that f of x equals y. Now that is the domain of f is all of y. Once you have the domain of f is all of y, then you can see that it's surjective mapping. Let's start for example. Now a function, let's look at this function. Function f mapped from a to b. You can have the domain of a being a, b, c, d, and then the codomain, that is b, x, y, z. And these are the arrow diagram. Show whether f is surjective or injective. Let's start with the first one. Surjective. Is this surjective mapping? Okay, the function is a surjective mapping. Why? Since for each y being a member of x, y, z, there is this a corresponding domain, that is a, b, c, d. such that f of x, and that's the fact, equals y. Then that is the range equals the codomain. Once you have the range equals codomain, then you can say that the function is onto. The function is onto. It's a surjective mapping. But can we say it's injective mapping? F is certainly no, it's not injective mapping. And the reason this z is having two elements from the domain, therefore it's not one-to-one mapping. Great. Bijective mapping. Suppose that x and y are two sets where the function f mapping from x to y is a function. Then f is bijective mapping when it is injective and then surjective. Once it's injective and surjective, then you can say it's bi means two, bijective mapping. Great. Next, for example, now let's see this function. You can see that I have domain here. Function f is having this domain, and then these are the codomain or the set of all images. So 1 is having image 1, 3, 2 is having image 3, 5, 3 is having image 9, and 4 is having image 11. Verify whether f is a bijective mapping. Now you have to look at the two cases. One, you check for injective. Is the function injective? Is the function injective mapping? Answer is yes. And why? Each element in the domain is serving a corresponding element in the codomain, or distant element in the codomain. You can say that is yes. That's two. We check if it is surjective. Okay, let's check. F is surjective since each element in the domain satisfy the rule f of y equals f of x, sorry, that is f of x equals, that is let me write with red marker, f of x equals to y. Then we can say that's surjective. With that note, we will say that this function or this mapping is actually a bijective mapping. And the reason is that the two conditions satisfied. Thank you. Session review. In this session, we look at definition of mappings. We also look at the various classes of mapping. And we say that the various classes of mapping are these. That is injective, surjective, and bijective mapping. Actually, when you add injective to surjective, you get bijective mappings. So thank you very much. In the next section, we're looking at compositions of mappings.